Okay, in this video I want to talk about matrix representation of a linear transformation that's also a linear operator. So a linear operator is just a linear transformation that goes from a vector space into the same vector space. So we can think about, if you look at this example I have written down, differentiation of a polynomial of degree less than or equal to 2 will spit out an answer that is also a polynomial of degree less than 2. Actually, it's smaller than that, but still, it'll be inside the same set. So if the domain space and the codomain space, the output space, are both the same vector space, then we might have it worded this way, where we're only given one basis. And that's supposed to mean that both your starting basis and your ending basis are the same thing, this particular B. Okay, so from the previous video, what we're going to do is we're going to take the linear transformation and apply it to each one of these vectors. Once we're done with that, we're going to find their coordinate matrix relative to the ending basis, which is also the same thing. So let's start by taking d applied to each one of these. So d of x squared, d is differentiation, so derivative of x squared would be 2x. d of x would be 1, and d of 1 would be 0. And then we have to write each of these as a coordinate matrix or a coordinate vector relative to this particular basis. So 2x relative to the basis b is going to be, well, how would you write 2x as a linear combination of these three? It would have to be 0 times x squared plus 2 times x plus 0 times 1. How would we write a linear combination for 1 relative to the b basis? Well, it would be 0 times x squared, 0 times x, and 1 times 1. And then d of 0, well, the only way to write 0 is as a 0 vector. And so our standard matrix for d, I'm going to use capital A, is going to be these three vectors, 0, 2, 0, 0, 0, 1, and 0, 0, 0. Okay, and reasons this might be helpful, what if instead of talking about matrices P2, I was talking about matrices P100, polynomials of degree 100 or less. I could find a matrix for that. What if I wanted to find a single formula for, like, I don't know, 72 derivatives of polynomials of degree 100 or less? That would be not too terrible to do that in MATLAB, because I could just take a single matrix, which shouldn't be too hard to find, and then take the 72nd power or 75th, whatever word number I said earlier, take a big power of it if I needed to. Okay, so anyway, this is how we would find the matrix representation of a linear operator. Hopefully it's also helpful, just reinforcing the ideas from the previous video of how do we find a matrix representation. We apply the transformation to our starting vectors. Whatever our answers are, we find the coordinate matrix or coordinate vectors of those. Those should be the columns of our answer. So we might want to write our answer this way so it's more obvious these three are columns.